What's up, guys? Welcome to part 3 about basic probability of a chance event. All right, we talked about experimental probability, trying to just do a couple trials to get a feel for the probability of an event occurring. Then we talked about theoretical probability. The true probability of an event will only reveal itself in the long run after we do many trials. And then we actually kind of started to dive into some rules, several different rules that apply when you're dealing with probability. And we ended with the addition rule, pretty big rule. But now we can continue to talk about some more rules. Let's talk about conditional probability. Now, we actually already learned about conditional proportions. This is no different. You should recognize the symbol here. The probability of A, then you see a line, B. What that means is we're finding the probability of A given that B is already known to be occurred. So this is conditional probability. This is very different than anything we've talked about thus far, but we did kind of mention this earlier in the year when we were looking at two-way tables. So once again, the back part's the most important part. That is the condition that we kind of know to be given, to have already been told. So these types of conditional probabilities are really easy with the two-way table. But what I did not show you a couple weeks ago was the formula for conditional probability is this. The probability of A on the condition of B can be found by finding the probability of A and B. Remember that upside down U stands for and, divided by the probability of B. Okay, numerator, probability of A and B, denominator, probability of B, divide them, you'll get the conditional probability. Let's show how this works. You should recognize this table because you just dealt with it in the previous video over do you wear glasses and what is your grade. All right, so let's find the probability that somebody wears glasses given that they are a senior. Okay, now I bet you could actually probably already get the answer very quickly. So if you actually do what I've already taught you a while ago, you're probably going to say, okay, the condition is the back part is the senior. So I'm only allowed to look at the 130 seniors. Of those 130 seniors, 34 of them are wearing glasses, so there's my probability. Remember, the condition changes your denominator. Since I know this person's a senior, I'm only allowed to look at the 130 seniors, 34 of which are wearing glasses. But I want to show you how my new formula can also get that answer. But listen, if this makes complete sense to you without a formula, by all means use it. But I want to make sure the formula truly makes sense to you guys. All right, so the formula says in the numerator goes the probability of glasses and being a senior. Okay, what is that probability? Well, if I look at all 500 students, 34 of them are both glasses wearers. I don't know if that's a phrase. They wear glasses and they are seniors out of 500. So again, the numerator is the probability that you reach into this group of 500 kids and you get a senior and they wear glasses, 34 out of 500. The denominator is the probability of getting a senior. That's the condition. That's the back part. And a senior, what's the probability I reach in and I get a senior? Well, there's 130 seniors out of 500 total students. So my numerator is both glasses and senior, 34 out of 500. My denominator is just the condition senior, 130 out of 500. Now watch this. Hopefully you guys know a little bit of algebra, because when you divide fractions, that's the same as multiplying by the reciprocal. So if I take the numerator, 34 out of 500, and instead of dividing, I multiply by the reciprocal, 500 out of 130, look what happens. The 500 cancels and we just get 34 out of 130, which is what we already knew the answer was. So listen, you don't need to use the formula in this situation if you understand, hey, the condition is senior. I'm only allowed to look at the 130 seniors. Of them, 34 wear glasses, 34 out of 130. But I really want to make sure you understand the idea of the formula is saying, all right, we first need to look at both glasses and senior. 34 out of 500 kids meet that qualification. Then in the denominator, we need to look at the condition, just being a senior. 130 out of 500. And then when you divide them, the fraction reduces, the 500s cancel, and you get that final answer that we know we needed. How simple and easy was that? So pretty simple, right? Pretty easy. Let's just do one more very quickly. What is the probability that you pick a sophomore given they do not wear glasses? Sophomore, given they do not wear glasses. All right, in the numerator is going to go both sophomore and no glasses. 52 sophomores and do not wear glasses. So 52 kids are sophomores that do not wear glasses out of 500. The denominator is not wearing glasses. There are 358 out of 500 kids that do not wear glasses. When you divide those, the 500s cancel and you get 52 out of 358. But again, that should make complete sense. Remember, the condition controls the denominator. So I'm only allowed to look at those that do not wear glasses. 358 total kids do not wear glasses. Of them, 52 are sophomores. There you go, 52 out of 358. Now, in this situation with the turkey, the actual formula comes in handy. So remember, all of these numbers are very specific. 62% of people have turkey. 65% of people do not have ham. This is 7% that have turkey and ham. This is 55% that have turkey and no ham, right? Very, very specific numbers. But what if I said, all right, you have turkey on your table. It's given that there's a turkey on your table. What's the probability that you also have ham? So this is not and, this is not or, this is a very different probability. You got to really read the question. What's the probability that you have ham on the condition given that you already have turkey? Well, again, this is where the formula is going to come in handy. The numerator is both turkey and ham. I'm following the formula. Numerator, both turkey and ham, 0.07. The denominator is the probability of the condition turkey. What's the probability somebody has turkey? Well, that is 0.62. Now, I'll get some kids that say, well, wait a minute, shouldn't that be 55% or no, whoa. Listen, back at the formula. The formula says the denominator is the probability of the condition. Don't worry about anything else, just the probability of that condition. So if the condition is turkey, what's the probability that there's turkey on somebody's table? I don't care about ham. I'm just talking about turkey right now. Well, that's 62%. So if you take 0.07 divided by 0.62, you get 0.113. You know, I like 3 decimals, so 0.113. So that means there's an 11% chance that if you have turkey on your table, you will also have ham. So very, very specific questioning. So lots of different questions that could be asked. Got to be very specific. All right, and this leads us to one more final topic for this video, independence. We actually talked about this quite a while ago as well when we dealt with two-way tables, but now it's going to make complete sense. Probability can also have us understand if there's an association between two categorical variables or not. So two outcomes, A and B, are independent only if this is true. If the probability of A equals the probability of A on the condition of B, then we could officially say that they are independent events. Why? Because on the left-hand side here, we don't care about B. Is it there? Is it not there? Did it happen? I just care about A. On the right-hand side, we're still caring about A, but we're saying, hey, we already know B was given to occur. So listen, if the probability of A given B occurred is equal to the probability of A, it just goes to show that B did not affect A. Makes sense. For example, what's the probability that somebody loves chocolate? Well, maybe we do a study, we find out that 35% of people love chocolate. Then we say, all right, let's still look at chocolate, but let's look at females. Of the females, what proportion love chocolate? Now, if it's still 35%, well, that means being a female had no impact on liking chocolate. That means they are independent. But if the probability of liking chocolate given you're a female skyrockets to 70%, well, obviously there is an association. Being a female directly impacted liking chocolate. So let's answer the question here. Is there an association between wearing glasses and your grade level? Well, let's figure this out. What's the probability that somebody wears glasses? All right, that's easy. 142 out of 500. 142 out of 500 is 0.284. And then we're going to say, all right, let's continue to look at wearing glasses. But let's see, does being a junior change that? So of the juniors, of the 155 juniors, condition changes the denominator, 32 of them wear glasses. So 32 divided by 155 is 0.206. So I think I have found, sorry for my messy handwriting there, that they are not equal. So apparently being a junior makes you less likely to wear glasses. So this is not independent. And look how simple of a formula it was for me to show that. If you're a junior, there's only about 20% of juniors that wear glasses, whereas of all kids, 28% wear glasses. So I don't know why. It's not my job to figure out why, but something about being a junior lowered your chance of liking glasses. Therefore, these two things are not independent. Being a junior is associated with wearing glasses. Actually, wearing less glasses, if that makes sense. So it's a nice, really simple formula that we can now verify, hey, if this is true, we can show that there is independence. All right, that's it for part 3. That is it for basic probability of a chance event. A lot going on. Be ready for some good practice.